So far, you've spent a lot of time learning about the metals on the periodic table. That class of elements that's so important for living things, for structures and technology. Metals are very, very important substances. However, the non-metal elements on the other side of the periodic table, even though they make up just a corner of the periodic table and not even half of the total number of different kinds of elements, they're very important too. One very important function of the nonmetals is that they make up DNA, the substance that builds up every single cell of every single living thing. Extremely important substances. Today, we're going to learn about the most reactive of those nonmetal substances, the halogens, which typically react with the metal substances on the periodic table to make different kinds of salts that are also important in technology, in medicine, and in living things. Let's begin by taking a look at where the halogens are on the periodic table of elements. And you'll notice the halogens occupy a column that's way over on the other side of the periodic table from the metals. The halogens make up the second to last column. And we're going to take a look at 4 atoms of halogens. The first one is fluorine, possibly the most reactive substance on the periodic table out of all of them. Next is chlorine, then bromine, and then iodine. Let's take a look at what makes these substances unique among atoms on the periodic table. First of all, it's important to note that the halogens all have 7 electrons that are far away from the nucleus, able to participate in bonding with other atoms. But the electrons of the halogens don't participate in the same way that the electrons of metals do. You see, there's this rule in chemistry that's pretty important for understanding why electrons and atoms behave the way that they do. We call it the Octet Rule. And what the Octet Rule says is that most atoms are most stable when they have 8 electrons in their outer shell. Now, the exceptions to this are atoms that are extremely light: hydrogen, helium, lithium, beryllium. They don't need a full 8 electrons in their outer shell, so instead of 8, they tend to only want 2 on the outside because they don't even have a big enough outer shell to contain 8 electrons there. So, however, all of the halogens are big enough to want 8. Now, let's think about that for a second. These elements each have 7 electrons in their outer shell. How are they going to get 8? The metals did it by getting rid of electrons. What are the halogens going to do? Well, they're going to each gain 1 more electron to make 8 in their outer shell. And notice what happens. When they gain that extra electron, because they're gaining an extra negative charge, these are becoming negative ions. And these negative ions are so reactive, they tend to bond with other atoms very easily. So usually we find the halogens in nature bonded to other atoms to make salts. Now, it's important to draw a comparison here. Do you remember the alkali metals, the most reactive group of metals on the periodic table? And how they formed those metallic bonds where the atoms would hold themselves to each other, but the electrons would be able to flow easily between the atoms? Reactive metals like the alkali metals, you never ever found them in their pure form in nature because they were just so reactive and those metallic bonds weren't enough to hold them together. They would just react with whatever they could. So that's what happens when metal atoms bonded to themselves. They would still be ridiculously reactive. On the other hand, when halogen atoms bond to themselves, they form a different kind of bond. Sometimes in nature, we find halogen atoms bonded to other halogen atoms, and those are fairly stable substances. Sometimes you'll find a chlorine atom bonded to another chlorine atom. It makes an extremely toxic and dangerous gas, but it's a lot more stable a substance than the alkali metals were. So just wanted to point that out. Halogens are completely different than metals. The characteristics of the halogens are important to note. They are extremely reactive and toxic to living things, so we oftentimes use them in medicine to kill bacteria, to sanitize medical equipment. Doctors will use iodine on your skin before they give you a shot to make sure that your skin doesn't have any bacteria that they're then pushing inside your bloodstream. Chlorine is used in swimming pools to disinfect the water. Oftentimes, halogens are used to kill living organic things because they're so reactive. Another important thing to note about halogens is they all have low melting and boiling points. In fact, chlorine and fluorine are gases at room temperature, and it takes quite a bit of work to cause them to condense to a liquid. Bromine is one of the elements that's a liquid at room temperature, and it's not very difficult to evaporate it into a gas. And iodine is a solid at room temperature, but it's also very easy to turn iodine into a gas. So these substances are very easy to melt and boil. In fact, 2 of them are already gases at room temperature. And then finally, they have the same properties that all nonmetals have. When they form solids, they are brittle solids that can be pounded and shattered. They do not conduct heat or electricity very well at all. And finally, they tend to have very, very low densities because they don't like to stick close together. These are the properties of the halogens on the periodic table of elements.